Yeah, good afternoon, everyone. So my name is Appala Naidu. I'm from CRM Institute, Hyderabad, and my co-author is Mrs. Renuka from IDRBT, Hyderabad. So I present my joint work on ECC-based common authentication protocol for IoT networks. So this is my flow of my presentation. Consists of the introduction, IoT security, and the architecture, and then the ECC cryptography with the cow selection, and our proposed protocol, and then the comparative analysis with the existing methods. So yes, all of us know that because of the advances in wireless communication and information technologies, we have a rapid growth in this development of the IoT, and this all the IoT devices that share the data through network between the sensor nodes to the gateway, and from there to the fog computing, and going to the cloud servers. So because of this complex networks, and because of the rapid number of the devices are increasing, so there is a major challenging is the authentication is the major challenging task. So there are several attacks already have been identified, and then majorly the traceability attack, and also man-in-the-middle attack, and replay attack is the major one is playing role. So coming to this, if you see this architecture, the IoT security architecture, we required like previous presenter mentioned, there are three security aspects: confidentiality, authentication, integrity is important. So our the motivation is to design a secure authentication based solution for IoT by using ECC and the YASH based functions. And then our proposal also will ensure the confidentiality of the identity by revealing the like without revealing any information about the device, and except the server. So anyway, I'm not going to cover about this ECC curve because importance of the ECC already is covered. So, but what kind of the selection criteria for ECC curves? Actually, why we are going to towards this, particularly for the IoT authentication and then later key exchange. Okay. So because of the smaller key sizes, because the ECC keys are much shorter than the RSA and DSA keys of equivalent strength. And then because of that, ECC algorithms are faster, because we require, particularly in the IoT environment, because of the low power and less memory, so we require a lightweight less computational functions. So ECC provides that, right? That's why we select either curves like from whatever the NIST curves given 160, or else we actually for our implementation we have selected the PE256 curve. So coming to our system model, if you see the system model is we have considered the IoT environment scenario consists of the communication parties. One is a server and the IoT device trying to communicate with the authentication through authentication, particularly with authentication in the network. The model which we have considered both passive and then active adversary model, where there is well-defined the capabilities of this Delove and AIOS model in the an IoT network, and having the access of the communication in the network. So here the server having the enough resources is responsible for allowing the genuine device for communication. And if user wants to communicate with the server, it must pass through the authentication process, right? So here the yes sends the challenge a message to the IoT device, then it is authenticated by the server, and later generate the session key, okay, between these two. So now I'm going to explain about our protocol having three phases. One is registration, second is login, and third one is authentication phase, followed by the session key agreement. So coming to the registration phase, here the server and device, interactively they share some information. Initially in the registration phase, a server generates randomly is a a secret key, and then calculate the curve point, that is GS equal to NS into G. Later the device, because we want to also assume, means also assure the the identity of the device not to be shared with the other parties and except the server. So server herself means himself will calculate the own ID. So that is IDI with the fixed ID plus some random number, that is RI into DI, and sends that ID to the server. Okay. So because some of the existing algorithms also, because they are not able to provide this what you call anonymous of this device, so we could able to provide by this, and then later the server receives that ID, and then it chooses some random number for each ID, and then compute the RD value, then finally stores all the values and accept that GS, it will send to, all other three values to the device. So now this is the registration phase. Secondly, the login phase, where here the device would like to log in means with the ID. It sends the ID to the server. Then the server means that retrieves the corresponding details of the particular ID. That is ND and RD values, and then randomly chooses the value N1 and compute the R1, which is again curve point. So that is R1 equal to N1 into G, and also it computes R1 dash. So that is NS into R1. So this R1 dash is going to be given to the each device. Now here, now the authentication process. If you see here, generally most of the existing algorithms, they provide the authentication at the server side, but in our case, we provide the authentication again at the like both sides. Server also will authenticate, also the each IoT device also will authenticate with the server. So first we'll see the IoT device authentication. So the device DI randomly generates N2 and computes the R2 value curve point. Again compute R3. And also computes the R4 value. So finally, it will also compute the authentication parameters, that is the V, which is the hash of the R3 plus R4, and it is going to send this value to the server S. So the V and R2 value is going to be shared with the server. Now the server is going to authenticate the device with these parameters. So the V dash is calculated, that hash of N1, NS, and then R2 plus ND plus R2. So finally, if it matches, then if V and V, so V, it has both matches, then the authentication is successful. Once if it is done, then again server calculates some values to share with the device for again, because the server also and has to finally they also have to prove themselves, so they will verify with these values. So initially the authentication, once if it is done at the server side, now the device side, the server is going to share the following information, like that is V1 and R5 values to the each device. So if each device again, if you see the step number 18 to again 20, again V1 dash will be calculated with the hash of ND into R5, because there is a verification proof also given in the next slides. So if V1 equal to V1 dash, then the authentication is successful at the device side. So once if these two are done, anyway the session key is being calculated at the step number 13 at server side, and at the step number 21 at the device side. If the authentication is successful, automatically the session key is being also verified at the both ends. So this is the server side verification proof, mathematical proof is given. So where V equal to V dash, and then for the device side verification also is being given here. And then once if these two are verified, and then the session key is agreed among these two parties, server and then the IoT device. So we have implemented, and then we also did a security analysis by using IVESPA tool, which is automated verification tool for the internet protocols. So our protocol, if you see that with the existing methods, the method and the corresponding the functions used in the design, that is ECC. First one is the ECC base, second one is the ECC plus hash, and ours also based on the ECC plus hash. So we could able to like means my proposal the proposed algorithm is is against to the standard attacks which we mentioned here. So man in the middle, reply attacks, and then impersonation attack, and message integrity attack, and then also that traceability attack. So this way we can say that the proposed method is more secure than the existing the five or six methods which were mentioned above. So coming to the conclusion, as I mentioned, that ECC-based authentication is considered for a protocol. This is because of the less computations, so people try to use these functions for a design of any authentication algorithms, and probably until the post-quantum the signatures are as a key exchange, people are trying to use these ECC-based functions for the authentication. So we would like to propose a new lightweight authenticated key agreement protocols. So this is our future plan. So any questions? So these are the references. Thank you.